We're going to begin now. Good afternoon and good morning to some of you that are in different time zones. Welcome to our webinar about TEMA, design of shell and tube heat exchangers. This webinar will be given by Javier Tirente, a senior mechanical engineer with a master's in business administration. He has over 20 years experience in the design, calculation, and production of mechanical equipment, such as pressure vessels, heat exchangers, storage tanks, piping systems, and other structures in general. He has extensive experience teaching specialized training courses, both in person and online. Javier is also an ASME authorized instructor. During this webinar, we will discuss the essential aspects involved in the design and manufacturing of shell and tube heat exchangers for industrial applications. We remind you that the webinar will be recorded and that it will be available on our YouTube channel, Arving Training and Engineering, starting tomorrow. At the end of the presentation, there will be a Q&A session where you can ask questions either through the chat or by using the hand raise feature in Teams, where we'll call on you and you can present your question directly to Javier. Now it's time to begin, so I'll pass things over to Javier. Good afternoon, Javier. We can't hear you. I'm sorry. I can't hear you.
Good afternoon, Autumn. Thank you so much for
Good
this kind
afternoon.
presentation. That is fantastic. So you are passing me the witness, so I can start. Thank you so much, Autumn. So hello, everyone. Good afternoon, good morning, good night, good evening, whatever applies to you all. Thank you so much for joining us today in this webinar. We are going to be talking about TEMA, shell and tube heat exchangers. And obviously, due to time constraints, we are not going to be able to cover everything that we would like. But however, we are going to be touching on some very interesting points. And the goal of this webinar is to answer some frequently asked questions, such as what types of heat exchangers are there? What is the difference between thermal and mechanical design? What are the most used mechanical design codes? What is the scope of TEMA standard? What is the terminology used to define TEMA shell and tube heat exchangers? And how are the different types of shell and tube heat exchangers grouped? So as you can see, these are very specific questions and we get these questions a lot. So we thought it might be a good idea to share them with you. And obviously, as I said before, we cannot cover the whole universe of shell and tube heat exchangers, but you're more than welcome to post your questions at the end of the webinar. And it is going to be our pleasure, my pleasure, to be addressing them and arriving to the adequate conclusions. So let's start from the top. What types of heat exchangers are there? Well, in order to understand the different types of heat exchangers, we can start by classifying them by the transfer type, how the heat is transferred from one fluid to the other. Because basically here we are going to be dealing with the heat transfer between two fluids. So if the transfer type is direct, if the fluids are in direct contact, that is one possibility of categories or classifying the equipment, the heat exchanger, in the different possibilities that we are going to find. The other alternative is the other alternative are the indirect contact type heat exchangers. Let's dig in a little bit more. Within the direct contact classification, there could be different options. For example, non-mixable fluids, gas liquid fluids, or liquid vapor. And then within the indirect contact, we have the subcategory of direct transfer and storage. And then again, in the direct transfer category, we have single phase and multi-phase. Let's clarify a little bit this and let's show some pictures. A classical example of very classical example of direct contact. Sorry for that. Okay, 1 second. Okay, there you go. So a very classical example of direct contact heat exchangers are cooling towers. In this case, we have two fluids that are interchanging heat. And in that case, the hot fluid is going to be the water that needs to be cooled down. And the cold fluid is going to be the air that is going to cool down the water. So there is a basic, very basic principle of cooling towers. In that case, we have direct contact. Let's move on to a classical example of indirect contact, air coolers. In this case, we still have two fluids. One could be water or hydrocarbons, and the other one is going to be the air. But in this case, the contact, there is no contact between the two fluids. That is why it is called indirect contact. And there's going to be, in this case, a tube separating both fluids. Another classification could be as per the construction. Sorry to bother you, Autumn. There is one microphone that is opened. I think there is some noise that is getting into the conversation. If you could mute that mic that is opened. Thank you so much. So going back to the construction type, um, another classification that we can make in order to understand heat exchangers is as per the construction type. So there could be tubular of tubular construction. It could be in the shape of plates. And there's also a group that is called extended surface. So those heat exchangers that are tubular, they could be double pipe, shell and tube, which is the reason why we are here today. And they also could be helical tubes. If we move to the plates category, plates and frame category, we are going to find PHE or spiral. And moving down to the extended surface category, we're going to find air coolers or cooling towers. Again, let's see some pictures and let's clarify with some examples. Within the tubular category, we have one type of exchangers that are the ones that are called hairpin. These are multitubular, where we have one element that is acting as a shell, in this case, one pipe. And inside the pipe, we have a tube bundle that is in the U shape in this case. And these heat exchangers are called or are known as hairpin. These type of heat exchangers can be constructed, can be manufactured in a very wide range of sizes, as we can see on the screen right now. Another type are the plate and frame type. In these heat exchangers, there are two fluids as it's been explained before. There are always two fluids in heat exchangers. There are two fluids that are interchanging the heat in the different plates that are arranged within the frame of the heat exchanger. A very specific characteristic of this type of heat exchangers is that they are very compact. They are very that they are saving a lot of space in terms of layout. On the contrary, they cannot operate with very heavy fluids or dirty fluids because of the very thin spaces within the plates or between the plates. So that is a characteristic. Another type of heat exchanger are the air cooler ones. As we can see on the screen, it operates with air as the cold fluid and the hot fluid entering into the heaters or the inlet heaters. The hot fluid could be water, hydrocarbons, or any other fluid. And that is basically the type of heat exchanger. And then we arrive to shell and tube heat exchangers. This type of equipment, these equipment are the objective of this webinar, and we're going to be discussing them a little bit more in detail. A shell and tube heat exchanger operates in the following way. As we've been mentioning before, there are two fluids that are going to be interchanging heat, and those two fluids in a shell and tube heat exchanger are arranged in the following way. There is one fluid that is going to circulate through the tube side. That is the fluid that is going to penetrate inside the tubes. It's going to return in some cases, and it's going to exit the tube side of the shell and tube heat exchanger. At the same time, we have the second fluid that is going to be circulating through the shell, and that fluid is going to be bathing the tube bundle with all the tubes that we can see on the screen. So that is how the two fluids are going to be interchanging heat in this device that is shell and tube heat exchanger. Shell and tube heat exchanger can be manufactured in a very wide range of size and number of tubes. For example, we can see on the left side of the screen, we can see a shell and tube heat exchanger that it has an inside diameter of 25 mils, and it has 24 very tiny, very small tubes. And in order to contrast this very tiny shell and tube heat exchanger, we can see a very large one within. We can see on the right side of the screen, we can see a shell and tube heat exchanger with an inside diameter of 4 meters. Housing for 4,200 tubes, which is a lot. And we can see that the length of this shell and tube heat exchanger is approximately 7.3 meters. So the range the range in which this type of equipment could be manufactured is very large, and that is why it's very sometimes challenging to arrive to the best design for the very vast and diverse options that we may find when it comes to designing a shell and tube heat exchanger. Okay, let's move on to the next fact. What is the difference between thermal and mechanical design? Well, first of all, let's say that the design process of a shell and tube heat exchanger follows at least two steps. The first one being the thermal design. During the thermal design, we are going to evaluate the heat exchanged and the required heat transfer surface in order to arrive to a specific geometry for that particular shell and tube heat exchanger. Once the geometry is defined, we are going to move on to the mechanical design. That mechanical design starts from a data sheet that is developed, and it is the output of the thermal design. So that data sheet is the starting point of the mechanical design. Once the basic geometry of the equipment is defined, we can move on and design or calculate the different components. In terms of evaluating the thermal design, and if we take one tube of the shell and tube heat exchanger, what we have is two fluids circulating normally, or the majority of the cases, in different directions. And what we want to evaluate is the energy that is going to be traveling from the hot fluid to the cold fluid. That is the whole point of this evaluation. And we're going to see that the energy is going to travel from the hot fluid by convection through the tube wall, by conduction, and then back into the hot fluid by convection, sorry. So with that in mind, there are a lot of equations and a lot of regions of the shell and tube heat exchanger that needs to be evaluated. Normally, nowadays, this evaluation is carried out, or it is done by means of specific software, calculation software, as you may know. Um, but anyway, let's bear in mind that software and specific calculation softwares were not available when the first designs or refineries were constructed. So there are alternatives to that. Nowadays, it is not thinkable, but it could be done. Anyhow, the output of this thermal evaluation or this thermal design, the output is going to be a datasheet. And this datasheet is going to contain basically two areas. One of them, it is going to show the output of the thermal analysis, indicated the flows and overall coefficients, transfer coefficients. Is going to show a lot of data that is going to be interesting from the thermal analysis point of view. But for mechanical designers or for the mechanical design, the important part is the preliminary mechanical design part. This part that is going to be one part of the output of the thermal design. It is going to be the basic geometry that is going to be used for the later stages of the mechanical design. So here we're going to find the basic shell diameter, tube diameters, number of tubes, distance between baffles, etc., etc., etc. We are going to find all the basic details necessary in order to carry out and to perform the mechanical design. So talking about the mechanical design, one of the questions that is normally on the table is the following: what are the most used mechanical design codes? Well, we're going to be discussing about the most used ones, but these are what we're going to see on the screen are not the only ones. These are the most used ones that normally we are going to be talking about American codes or North American codes and standards. First of all, we need to clarify that there are going to be two sides of the story when it comes to the mechanical design. One is going to be the mechanical design itself in terms of requirements or limitations to the geometry, sizes, materials, etc., etc. And then we are going to have codes for the pressure design of the components. So on the one side, we have geometry, tolerances, materials, and that kind of requirements. But when it comes to pressure design, there are most design codes that we are seeing on the screen are complementary to the ASME code. So let's start with TEMA. The Tubular Exchangers Manufacturers Association, or TEMA, it is the most used standard in terms of designing and specifying a shell and tube heat exchanger. So we're going to find requirements in terms of size, tolerances, and procedures to develop the overall design of the shell and tube heat exchanger. But when it comes to pressure components, TEMA code is going to direct us to the ASME section 8, division 1 or division 2 or division 3 code for pressure parts. The same happens with the HEI standard, Heat Exchange Institute. At the same time, for chemical or petrochemical, or sorry, chemical or pharmaceutical industries, most likely we're going to be using the HEI, or for power generation projects, we're going to be using HEI standard. And we are going to find all the requirements in terms of geometry, minimum thicknesses, and materials, for example. We're going to find them in HEI. But when it comes to pressure design, the standard is going to direct us to the ASME section 8 code. Could be division 1, division 2, depending on the case or depending on the project. It is worth mentioning that there are also some other standards applicable to specific industries, as the API 660 specification. It is a specification that is applicable to oil and gas. If we are talking about oil and gas, it is very likely that we are going to be working with API 660. Or for specific designs, there is one section in the ASME 8, that is the part UHX, that is dedicated to the design of some parts, for example, the tube sheet of shell and tube heat exchangers. The reason behind this is that there are some equipment that are going to be stamped. In those cases, there are some components like the tube sheet, for example, that need to be designed and manufactured as per specific rules of ASME Section 8, Part UHX. Great. Let's move on to the next fact. What is the scope of the TEMA standard? And we're going to be talking about TEMA, as I said before, because it's the most used overall, is the most used standard for the design, for the mechanical design of this type of equipment. As simple as that. And that is why we are covering this standard today. In terms of the scope and limitations, what type of equipment can be designed under this code? Well, in terms of diameter, the limit that the TEMA standard is setting, it is 100 inches. The inside diameter of the shell and tube heat exchanger needs to be under 100 inches. This is 2,540 mils. In terms of pressure, needs to be under 3,000 psi. This is 210 bars. And there is also a limitation that is a product between the pressure and the inside diameter, that it is a consequence of the two above. So it is a little bit of a nonsense, this one, according to me, of course. But I do not pretend to know more I do not pretend to know more than the committee that drafted the TEMA standard. So we include it, of course. It is important to bear in mind that the goal to this limitation is to limit the shell thickness up to 76 mils, and the diameter of the bolts that we are going to be using in order to join the flanges. The idea is to limit those bolts below 100 mils. However, this limitation, it is a suggestion. There is no prohibition within the standard in terms of thicknesses and bolts diameter. So what I'm trying to say here is that this code could be applied to larger equipment with restrictions and with further considerations or with some further assessments of the design and the calculation. Great. Let's move on to the terminology. What is the terminology used to define TEMA shell and tube heat exchangers? Well, when it comes to terminology or designation, TEMA divides a shell and tube heat exchangers in three main components, let's say. These three main components are the three columns that we are seeing on the screen. The first component, it is the stationary head type. This is the first column or the first item that is defined by TEMA. The second component is the shell type. There are many different types of shells that can be used with one pass, two passes centered, many different types of shells. And by the same token, we have the rear head types. These rear head types are going to allow the shell and tube heat exchanger to behave in a different way. Well, actually, the all the all the alternatives on all three components are allowing, obviously, or are permitting the equipment to achieve different behaviors um, and to operate with different fluids, temperatures, etc., etc. So how does this designation work? Well, the designation is very straightforward. Depending on the operating, maintenance, and depending on the design requirements, the designer is going to select one alternative or another in terms of the three different groups that we are seeing on the screen. And that being said, for example, if the selection is made for the stationary head type A, shell type E, and rear head type M, we are going to arrive to a shell and tube heat exchanger that is going to be AEM, and that has obviously different connotations. Um, a, and a shell, a shell and tube heat exchanger that is AEM is going to have only one pass on the shell. It is going to have one blind cover on the stationary head for maintenance, something that we cannot find in the B category, for example. And it's going to have a rear type that is going to be able to attach directly to the shell, for example. I am just mentioning two or three things for us to understand that every selection has a connotation, and we are going to have obviously some characteristics derived from that selection. Okay, let's move on to the groups. How are the different types of shell and tube heat exchangers grouped? There are mainly three groups of shell and tube heat exchangers, mainly. Being one of them, the fixed tube sheets group. We have the U-tubes group. And then we have the floating tube sheets group. Let's go a little bit into more detail with these groups. The shell and tube heat exchangers with fixed tube sheets and straight tubes, obviously, they adopt configurations as we can see on the screen, BEM, AM, NEN, as per the TEMA designation. Then what can we say about these types of channel tube heat exchangers? Well, the construction, it is simple, simple compared to the other ones, to the other groups. And um, that simple construction comes with advantages and disadvantages, of course. Um, they are the more economical ones compared to the other groups. However, they do not allow differential thermal expansion between the tube bundle and the shell. Since the tube sheets are fixed, there is one group of components there. So the tube bundle cannot expand in a different way than the shell. That is a huge disadvantage for this type of equipment, especially high temperatures. Let's move on to the next category, U-tubes. U-tubes are mainly used for removable bundles. The tube bundle is what we are seeing on the screen, as you very well know. The configurations as per the TEMA designation that can be obtained with this are AEU, BEU. It is very logical, and it was not needed to come to this webinar to understand that the U at the end, it is indicating a U bundle, U-tubes bundle. So normally the U-tubes indicate a lower cost for the bundle, for the construction. And again, this presents advantages and disadvantages. Fabrication, it is simple compared to the floating category. It is simple. And one disadvantage, it is that these curved tubes require a specific procedure in terms of avoiding wall thinning of the tubes. So that is a little bit tricky and complicated. So it is something to take into account. And finally, we have the floating heads category. In this case, we are going to find that the TEMA designation, it is normally going to be AES, BES, are used for frequent removal of the tube bundle. The removal of the tube bundle, it is very easy with this type of channel tube heat exchangers. And one advantage is that the differential thermal expansion between the tube bundle and the shell, it is guaranteed in this case. So it is recommended for high temperatures, this type of channel tube heat exchangers. And as a disadvantage, we can mention that there is a much higher cost of maintenance for this type of channel tube heat exchangers. So sometimes this makes the selection or the use of this type of equipment a little bit more, let's say, difficult, because they are more expensive and more difficult to maintain. So up to here is what we have prepared for you, and what frequently asked questions we wanted to discuss with you. Right now, I'm just going to stop sharing my screen, and I'm going to invite you to raise your questions. And Autumn, if you are so kind and you can coordinate this part, will be great.
Of course. Thank you for the presentation, Javier.
My pleasure.
Um, so now it's the time for Q&A. You can send questions through the chat or use the hand raise feature to participate. And let me just make sure I didn't get any messages during the time. Hold on. I did get one by email that I
Great.
will give to you. It says, if there are no specific calculation tools available, is it possible to carry out the thermal design manually?
Very good question. Very good question, Autumn. Um, it is possible. It's been done for many, many years. And I am aware that for some very specific and brief verifications, it is done. What I am referring to, it is manual calculations, hand calculations. We are dealing with here. We are dealing with thermodynamics. So this is just physics, and there is no reason whatsoever why we cannot perform manual calculations. Obviously, that nowadays with the tools that we have, most of the times it is not wise to do it that way, time-wise, but can be done. It's been done and can be done.
Sorry, I was on mute. One question we received in the chat, how much leak tubes shall be blocked without affecting efficiency?
Very good question, Salim. Salim Khalid or Salim Khalid. I hope I am pronouncing your name, sir, roughly correctly. That is a very good question, and that is a question related to, let's say, maintenance and repair of shell and tube heat exchangers. That is related to ASME PCC2, for example, or API 510. Those are design codes that are regulating or are indicating, giving a rough figure of the number of tubes that should be blocked. There is an indication in ASME PCC2 that show us a recommendation actually that show us which percentage it is advisable um, for the owner to operate the shell and tube heat exchanger with blocked tubes. It goes from 20 to 50%, but that is just a suggestion. It is nothing mandatory. And I've seen shell and tubes, heat exchangers mm, operating with a very large number, a very large percentage of tubes blocked. So unfortunately, there is obviously that not only that is outside the scope of this webinar, but there is no a specific number or figure that indicates what is the maximum amount of blocked tubes. But
Oh,
PCC2, it is the source to be checked.
okay. We have another question from Alex. He says, when you mentioned power generation system, did you mean hydrogen activities, or in this case, we need to use HEI standard? Is there any limitation in this standard, or is it still under development?
Very good question, Alex. Thank you so much for that. HEI, normally, I mean, if you go to the scope of the HEI standard, you're going to see there the phrase power generation. You are not going to see hydrogen, but you're not going to, as far as I know, you're not going to find there that hydrogen, it is forbidden or is excluded from the scope of that standard. In my opinion, shell and tube heat exchangers for hydrogen service are a little bit outside the scope of HEI because of the complexity and the difficulty that hydrogen, due to the size of the particle or the molecule, the challenges that presents in terms of material selection, it is not going to be covered by the HEI, but right now, hydrogen is used in refineries. For example, it is not green hydrogen, but it is hydrogen. And HEI, it is not used for those shell and tube heat exchangers. TEMA, IASME, and API 660 is used for those cases. So that is basically the answer in a nutshell.
Great. Miguel also has a question. Is there a general rule of thumb for the placement of fluids in the tube/shell side?
Very good question, Miguel. There are different thumb rules. This is related to the thermal design, and normally the fluids are arranged in terms of the ones that need to be cooled down. Um, there are there are rules, or there is one rule of many engineering companies that indicate, or process engineering companies that indicate, that the fluid to be refrigerated needs to go in the tube side. But at the same time, there are some other companies or sound engineering practices that indicate that for specific fluids, the ones that need to be cooled down need to go on the shell side. So there are thumb rules or sound engineering practices, but they need to be analyzed on a case by case basis for the group of fluids that we're working with.
All right. We also received another question from Salim. Um, is DHT heat treatment of welded tube sheets effective for weldability?
Very good question, Salim. I can see that you know your stuff. I can see that you know the game. You're very on the money, and very specific questions. DHT, dehydrogenation, heat treatment. A very tough word for me, as you can see. Um, that is very specific to fabrication, and it is effective for weldability. Well, it is effective depending on the materials that you're using, the welding procedure, the temperatures. There are many factors involved. And also we need to mention that it also depends on the client if you're going to be allowed to be using DHT or not. Not every specification allows the use of DHT. So very good question, but there is not a very, let's say, overall answer or a very specific answer that can cover the many scenarios. It depends, but it is effective. In many cases, it is effective.
Okay. Were there any other questions here? Because if not, I have some emailed ones that I can go to. Okay. One that I received is, how are the TEMA standard and the ASME 8 code related?
Good question. Good question. It that question appears a lot, and it is asked a lot. So we need to bear in mind that when we are designing a shell and tube heat exchanger, there are going to be at least two design codes that are going to be involved. One of them is going to be TEMA, and TEMA is going to be uh, listing and providing all the requirements in terms of sizing, minimum thicknesses, tolerances, machining, so on and so forth. But then when it comes to the pressure design of pressure parts, if you go to section 321, I think it was, I don't remember right now. If you go to a specific section of the scope of the TEMA standard, that is going to guide you, or it's going to indicate us to go to ASME section 8 code. So when it comes to pressure parts, TEMA is going to direct us to ASME. So that is the relationship that exists between those two codes, in this case, the ASME code and the TEMA standard. Good question.
Yep. Um, well, we haven't received any more for chat, but I have one last one via email. It says, from the point of view of structural stability, what would be the most important element of an S&T heat exchanger?
Good question, and not an easy one. Not an easy one. Um, as with any calculation that you are performing, there are different components that you might anticipate that they are the most important ones for the structural stability. But overall, without a doubt, the tube sheet of a shell and tube heat exchanger, it is going to be the component that is going to bring uh, it is going to be the most important one in order to guarantee the structural stability of the equipment, without a doubt.
Okay, well, I think that's all the questions.
Good, good,
Thank
good.
you. Thank you so much for the presentation, Javier, for
They,
answering the questions.
it's been truly a pleasure. Thank you for hosting this webinar, and thank you everybody for joining us and for raising and posting very, very interesting questions.
Yeah, and just a reminder that the recording of the webinar will be available, um, starting tomorrow on our YouTube channel, and you'll get an email about it with a link. Okay.
Okay,
So,
and just a reminder from my side, if you are interested in knowing more about shell and tube heat exchangers or pressure vessels or piping systems, or if you have a specific need that um, you need somebody to ask, or you need a different point of view or whatever, feel free to send us an email, and we are going to do the best in terms of helping you, and there's always a solution that can be found. So thank you so much for joining.
thanks everyone. Bye.
Bye bye. Thank you. Bye.